Hey class, and welcome back. And we're now going to cover the second half of chapter 7. So we just left off talking about conservation of momentum, right? And this idea that if you have an isolated system, the total momentum of all members of your system together will not change or will be constant. So we're going to now look at what happens then as we apply that to various different situations and defining different things like elastic and inelastic collisions, and then also looking at conservation of momentum when you have things moving in multiple directions at the same time. So 2D conservation of momentum as well. So here we go. So I want to talk about different types of collisions. So if you notice, when we're dealing with conservation of momentum, we're really looking at collisions when different things are transferring their momentum between two objects as a result of a collision. And so we are going to kind of put collisions into one of two categories, or really three, I guess, to be most thorough. Three categories. So the first type of collision is an elastic collision. And what it means for a collision to be elastic, it means that all of the kinetic energy before the collision is equal to the kinetic energy after the collision. So what that means is not only would momentum be conserved if you have an elastic collision in an isolated system, but you would also have kinetic energy being conserved. Now, an inelastic collision, or a completely inelastic collision, is where kinetic energy is lost, and so it is not conserved. And an example of a completely inelastic collisions is if the two objects collide and stick together as a result of their collision. So that's a completely inelastic collision when they stick together. And so the vast majority of collisions will fall between these two. It will not be elastic because some kinetic energy is lost, but it will not be completely inelastic either because the objects don't always stick together. So any other collision, like a baseball bat with a baseball, or a bouncy ball bouncing off of a floor, or any of those types of things, would be considered a partially inelastic collision, where you have a loss of kinetic energy, but the objects do not stick together. So elastic is the special case where kinetic energy and momentum are both conserved. Completely inelastic is stick together, and then partially inelastic is everything else. So again, just to kind of show you examples, if you had a collision with springs, two things bouncing off of one another, the springs would be able to store and return energy, so that would be pretty much an elastic collision with almost no loss in kinetic energy. And then an inelastic collision, a completely inelastic, is if you had two things stick together with Velcro as a result of their collision. So some cool things happen when you have elastic collisions, and that's why we're going to look at them. All right. Now, in reality, you're always going to probably have some amount of lost energy, but there's certain applications where you can approximate collisions as being elastic, especially on the small scale when you're looking at collisions between atoms or air molecules and similar. So if you have a completely elastic collision, for example, if one of your masses starts at rest and they collide elastically, using the combination of conservation of momentum and conservation of kinetic energy, you can get some really simplified equations. For example, you can solve for the final velocity of the second mass, the one that starts at rest, as being simply equal to 2 times the first mass divided by the total mass of the system multiplied by whatever the initial velocity of the first mass is. So the simplified equation comes directly from conservation of momentum and conservation of kinetic energy. And similarly, you can solve for the final velocity of that first mass as being the difference in the mass over the total mass times the initial velocity of object 1. Pretty cool, right? Very simplified equation. So given what the first velocity is starting with, you have two different equations here. So you could solve actually for both mass 1 and mass 2 simply by knowing the velocity of your first object. Or even knowing the velocity or the mass of the first object, you could find the velocity and m2 or whatever the case may be. You can solve for a lot of cool things quite simply by knowing just a few variables. So this all assumes that the second object is at rest when you start. Now if you have an elastic collision and both objects are moving, again using conservation of energy and conservation of momentum, you get the more generalized case. And if you notice these equations that you can derive, again, the algebra gets a bit ugly, so I'm not going through all the steps, but you can derive these just starting with conservation of kinetic energy and momentum. You notice these two equations are the same as what we saw before, only before V2 initial was 0, so this whole last term was left off of both of these. But so these are the more general equations, and you're welcome to put these on your equation sheet if you would like. So go ahead and use these, but again, keep in mind this is assuming you have an elastic collision and both objects are moving in the same direction. So it's in one dimension and elastic. It's a special case, but it's a cool special case. So let's do an example with this one, all right? So imagine two titanium spheres are going to collide together. When they collide together, that will be a nearly elastic collision. So let's approximate it as being an elastic collision. Let's assume they collide head-on in the same direction, moving at the same speed. All right? Based on that information, I will tell you one of the two spheres has a mass of 600 grams, and that object will stop as a result of the collision. So they come together, one is 600 grams, they're moving at the same speed, they hit, and that one stops and the other one bounces off. You don't know what the initial velocity is, you don't know what the final velocity is, and I want you to find the mass of the second sphere. Not a lot of information, but pretty cool. Try it out. Ready, go. Here's our two equations that we just had. Hopefully you tried it out, hopefully you paused it. I'm going to go ahead and work through the solution now. So, here's our equation for the final velocity of object 1. Now object 1, I'm calling the 600 gram mass, and I was told it stopped as a result of the collision. So its final velocity is 0, its mass is 0.6 kilograms, and the only other bit of information I'm given is that they start with equal and opposite velocities. I don't know what that velocity is, but they are equal and opposite. Okay? From there alone, you can solve for mass 2. Let's check it out. So we know that it starts with that the final velocity of mass 1 is 0, and so 0 is equal to this whole ugly thing. At first glance, it looks like, how are we supposed to solve? This is crazy. Well, let's multiply through by the total mass, m1 plus m2. 0 times m1 plus m2, still 0. So that gets rid of those guys. I also observe that v2 initial is just the negative of v1 initial, right? So now I can divide through by v1 initial. 0 over v1 initial, still 0. Don't forget this negative sign though. So I'm going to pop that negative sign up. And now I'm just left with 0 equals m1 minus m2 minus 2m2. So solving 3m2 is equal to m1. m2 is just m1 over 3, or 200 grams. Boom. Pretty simple example. Pretty cool. Pretty box-worthy. All right. So now when you get into 2 dimensions, when the objects bounce off of one another elastically, all right, it gets a bit more complicated. As they bounce off elastically, you can get a lot more tricky stuff going on because you have to think about momentum in the x direction and momentum in the y direction. So if we have a situation like this where object 2 starts at rest, object 1 collides with it, and they bounce off from one another, you're going to have to do everything in component form. So your initial momentum is only in the x and it's 0 in the y, but you got all these sines and cosines. But again, that's what it will look like if you're breaking it down into 2 dimensions. The cool thing happens though, when you combine kinetic energy, you can add in the conservation of kinetic energy, and one really cool thing happens, there's others, but one really cool thing, if these two masses happen to be equal to one another, if and only if those two masses are equal to one another and mass 2 starts at rest, guess what? No matter what, every single time, theta 1 plus theta 2 will equal 90 degrees. So the total angle that they make, if their masses are the same, always 90 degrees. Pretty cool. Super useful in billiards especially. So yeah, pretty fun. All right, so before moving on to the kind of the last new topic and application of momentum, I want to talk about one more example. So a cool thing used by forensic scientists is known as a ballistic pendulum. This was used even more so in days of old, a little bit still. But basically, it's a setup where you can determine the speed of a bullet. So if you were to fire a gun into a block of wood and observe how far those two objects swung vertically with one another, you could determine the initial velocity of the bullet. So I want you to do that. I want you to help out the forensic scientists. They come and hire you because you know your physics, and they say, all right, we can find the mass of the bullet, we can weigh it, right? We can put it on a scale and find its mass. Same thing with this block of wood, all right? So knowing just those two masses and being able to observe the height that the block and bullet swing together as a result of this collision, I want you to calculate for me what is the initial velocity of the bullet. But since they want you to derive the equation for them so they can use it all the time. So do it just in terms of variables. For any MB and MW and any H, what is the initial velocity of the bullet? So keep in mind, the bullet starts moving, the block of wood stationary. They then collide and stick together. Both of them move together and swing up some vertical height h. Solve for v, the initial velocity of the bullet, in terms of the masses and h. Ready, go. This is a tricky one. Pause it, try it out. All right, hopefully you tried it out. And it's tricky, right? You're trying to figure out what's going on. How do I find the velocity? Well, you need to realize that there's really 3 points in time to consider. Point 1 is when the bullet's moving and the block is not, before the collision occurs. Then you have point 2, which is after the collision occurs. What type of collision do we have? Well, they stick together, so it's a completely inelastic collision. That means energy will be lost. Don't forget. And then you have point 3 after things have swung up all the way. So from point 1 to point 2, we have a collision. So that immediately makes me think about conservation of energy. Or sorry, conservation of momentum. I already told you energy will be lost. So we can't use energy. So from 1 to 2, we're going to use momentum. All right? Because we have a collision where energy will be lost. Then from points 2 to 3, we're having an object that's moving, swing up to some new height. Momentum won't help me there. There's no collision or anything, so that makes me think of conservation of energy. So from point 1 to 2, I'm going to use conservation of momentum. Point 2 to 3, I'm going to use conservation of energy and try to solve. So let's start with point 1 to 2, since we want the velocity of the bullet, and that's moving at point 1. So initial velocity in the x is equal to final velocity in the x. My total initial momentum will be the momentum of the wood plus the momentum of the bullet. And that's going to be equal to the total momentum of the two when they stick together after the collision. So this capital V down here, I'm calling V2 in the x direction. So I notice the velocity of the wood initial at point 1, that's just 0. So all I have is the momentum of the bullet equals the momentum of the two together afterwards. That's easy enough. Solving for the velocity of the bullet, it's just going to be the total mass over the mass of the bullet times this velocity at point 2. But we don't know what that velocity is, so we can't solve just yet. So instead, we need to move on to looking at chapter 2, or chapter 2, part 2, which is looking at points 2 to 3, conservation of energy. So conservation of energy. What kind of energy do we have at point 2? Well, we have kinetic energy, 1/2 the total mass times that V2 squared, because they're moving together at that point. At point 3, it's now stopped but moved to some new height, so it's just going to have gravitational potential energy, mass times g times h. So I notice at first, boom, my masses cancel out, and I can multiply by 2, so V2 squared is just going to be equal to 2gh. Take the square root of both sides, and V2 is just the square root of 2gh. I can now plug that into my equation up here, and I find a box-worthy equation. The velocity of the bullet will always be equal to the total mass divided by the mass of the bullet and then multiplied by the square root of 2gh. Super cool application, right? Good stuff. All right, so the last thing I just want to kind of throw at you all as an understanding and a conceptual sort of example of conservation of momentum, and that's the concept of rocketry. So if you think about it, how do rockets propel themselves forward? All right, you see that jet shooting out the back. Sometimes people think, oh, they're like pushing off the ground. You see that jet shoot off the ground and that launches them upward. But they work super well out in space too, where there's no ground, there's no air to push off of and different things. How do they work out in space? Well, it's really about momentum. You can think about it in terms of Newton's third law, equal and opposite forces, but you can also think about it in terms of momentum, right? How do the rockets propel themselves? Well, they use conservation of momentum. They shoot gas out the back at high speeds. It's not super massive, but it still has mass. So coming out the back, there's some momentum that the fuel has as it's being shot out. And so because of conservation of momentum, when the rocket's up off the ground, it's an isolated system. And so therefore, it's going to have an equal amount of forward momentum. But if you think about it, fuel is very lightweight, right? And so you're going to have to give lots of fuel out the back with lots of speed to get your rocket going in the opposite direction because it's so much more massive. But again, if you think about this, the total net change in momentum is always going to be zero, right? So if you had a rocket, or even like if you blow up a balloon, you hold it out and you let it go, right? Its initial momentum will be zero. You let it go, the final momentum is zero also. You have gas shooting out one side and the rocket or the balloon going in the opposite direction with equal amounts of momentum, just like the gun example we did in the last video. So you can actually calculate using one of the rocketry equations, and really starting from calculus and doing a little integration, but you can calculate the maximum possible speed a rocket can achieve. And that maximum possible speed that it can get, so V, the subscript S represents like a ship, okay, so the rocket ship versus the fuel. The maximum speed it can achieve is just going to be equal to the negative natural log of the total mass that you have of your fuel plus your ship divided by the mass of the ship and multiplied by the final velocity. You get this natural log because the total mass of the ship changes with time. As you're shooting out more and more fuel, you're decreasing the amount of mass you're having to accelerate. So therefore, you have to integrate as it changes. Anyway, just to give you an example, typical speeds that you can eject fuel at are in the ballpark of 10,000 miles an hour. To be able to escape Earth's gravitational well, you need your ship to achieve speeds of somewhere in the ballpark of 22,000 miles an hour if you wanted to head to Mars or to infinity and beyond, as Buzz Lightyear likes to say. So guess what? How much fuel do you think it would take to actually achieve exit velocity? What percentage of your overall payload, of your overall starting mass, do you think would need to be fuel? Would it be 50, 75, or 90%? You can pause and try to plug it in, right? You don't have actual numbers, but say you're doing 75% fuel, then just put 75 for the fuel and 25 for the ship, because that's 25%, and see what you get. What you would find is you need to get up to about 90% of your overall payload needs to be fuel in order to achieve exit velocity. That's pretty crazy. You got to get going super fast in order to escape Earth's gravitational well. So that's kind of a fun side note and a side application, but this is derived directly from the idea of conservation of momentum. Anyway, I'm going to stop it there because that really wraps up the concepts from Chapter 9. And again, tune in future videos for more detailed example problems from both the first and the second halves of Chapter 9. Other than that, have yourselves a box-worthy day.